Welcome back to this session about deep learning and Boltzmann machines applied to quantum mechanical calculations. So I'm going to repeat some of the things we did last week, but I'm also going to put these topics in connection with the neural network calculations and the way these Boltzmann machines are used in machine learning. Now, there's a reason for why I'm going to do this. So one, it gives you the overarching view on how Boltzmann machines have been used in machine learning. But then what I wanted to motivate with that is that the calculations we are going to run are much simpler than those you will run with a standard Boltzmann machine. So Boltzmann machines, when it comes to deep learning, are what we would say nowadays outdated. They are, however, interesting for us because they allow us to implement our deep learning methods using the whole framework which we had from Project One. So the only thing we are going to need is to change the derivatives of the wave function, the trial wave function, the trial wave function itself, and we need some small additional elements. But in order to see the simplification, it is actually useful to understand the basics of a deep learning model like a Boltzmann machine. So a Boltzmann machine belongs to deep learning models, which are called generative models. So generative models are the fashion nowadays. So everybody here has probably used ChatGPT. And ChatGPT is an example of a generative model. So what you're doing then is that you're training a probability distribution based on some input data. In our case, the input data are going to be the positions of the particles. And then we are going to train a probability distribution, which is a wave function squared, right? So Boltzmann machines, therefore, they lend themselves to extremely simple interpretations for us. And from a pedagogical point of view, it's actually one of the simplest ways of implementing a deep learning method in quantum mechanical calculations. So you will see, and you probably saw that last week, that there are simply some simple elements which you need to add. However, I wanted to give you a little bit of the background of Boltzmann machines, and then you will also see why they have lost a little bit of the impact they had in the end of the last millennium, or I should say last century, because last millennium sounds like eons ago. But when I say last century, I mean, it sounds a little bit easier. And probably some of you were not born in the last century either. So I'm a guy from the last century, as you probably have seen. So one of the reasons why they have been abandoned is something you will see quickly. However, right before COVID, people replaced this energy function, which we will be discussing today, with a neural network. And this led to actually the basis for software like DAL-E, which probably some of you have used to generate images, ImageGen, which is another software. So if you replace the energy, which you're going to see in the Boltzmann machine now, with a neural network or convolution neural network, this has been extremely popular in training in the last 2 to 3 years. Now, this development in generative models is so fast that a software like DAL-E for making images, which was very popular 1 or 2 years ago, is just been superseded by other models. But you will see now that this kind of training of Boltzmann machines is something which has flexibility nowadays, which goes beyond the simplicity which we will use. Now, Boltzmann machines were also used for imaging before CNNs, convolutional neural networks, really took over. And in 2000 to 2010, there was a lot of research on this type of models. And you will recognize many of the kind of physics-based modeling. Now, there's another thing with Boltzmann machines. They link with Markov chain Monte Carlo methods. This is the way you actually do the sampling. We are going to stick with metropolis sampling because that is efficient for quantum mechanical calculations, since we are taking the ratios between wave functions. And when you take the ratios between wave functions and you move one particle at a time, that ratio is easier to calculate. Now, in standard Boltzmann machines, people use something which is called Gibbs sampling, which requires that you calculate the conditional probability. Now, in the slides, you will see the derivation of the conditional probability. We don't need that in project 2. So that's another simplification. So in a standard Boltzmann machine, you will need what in statistics is called the marginal probability, which in our case is going to be the probability of being in a position X, but where we have integrated away additional degrees of freedom. And we will also need the conditional probability, which is needed in order to find how a network is going to fire, whether it fires or not. So I wanted to give you some of these kind of basic elements of the Boltzmann machine, and then we just turn the attention to the simplification, which we have in our case. So you will see that there is a possibility of replacing a Boltzmann machine with a deep neural network. So this is the kind of research which I'm dealing with. But that is is a little bit more complicated, and it moves quickly into a Master of Science topic. So we have roughly 10 credits here, and this will be, the project will be 5 credits roughly. So replacing a Boltzmann machine with a standard deep neural network, it can be done, but it would take more time. So when Carleo and Troyer, the people who actually reintroduced Boltzmann machines in quantum mechanical calculations, used Boltzmann machines, it was simply due to their simplicity. So I'm trying to demonstrate to you why the quantum mechanical calculation is simpler than the application of a standard Boltzmann machine. Okay? So I wanted to show you first the standard way by which Boltzmann machines are used and what kind of training you actually do. So one of the things which we did, so I'm going to use the slides here. So these are normally called energy-based models. And these type of energy-based models, let me just do the full screen here. So this type of energy-based models, they assume that you have a probability distribution and your different stochastic events are assumed to be identically distributed and independent. That's a pretty common. Then you can add additional degrees of freedom, which are these hidden layers. So that gives you more flexibility in the optimization. So keep in mind that when you do a typical neural network, you have visible input and visible output. So these are the things you relate to, right? These are the data you have. And in between, you have some black magic taking place. And this is often replaced by variables, which you optimize, which we normally call hidden variables. This was actually introduced back in the 70s in quantum Monte Carlo calculations, but then it was called shadow wave function. And since we have people from the University of Trento, there is one of the professors there, Francesco Pederiva, who has been using these shadow wave functions before people introduced the Boltzmann machines. But in essence, it ends up being almost the same. Okay, so what we have then is the probability distribution. So let me just, not that one, but this one. So if you now take the full model, you can think of xi as the position of the system. So if you have 2 particles in 2 dimensions, xi represents an object which contains 4 variables, x and y for particle 1, and x and y for particle 2. So you can read this xi in different ways. Now hj is then the so-called hidden variable. And normally when you represent this as a network, you would have some nodes. and the nodes are then representing, let's say, the positions of the particles. And then you have some hidden layers as well. Now, when you do physics, you're not interested at the end in the hidden variables. So that means that you're going to either sum up over these hidden variables or integrate them away. Because at the end, you want to have P of X. That is the probability of being in a specific position. And if you think of what you did in project 1, P of X is your wave function squared, right? And that's your probability. So when you do quantum mechanics, life is in a certain sense a little bit easier when it comes to the interpretations of the probabilities. Now, if you go back a little bit to the previous slide, when you optimize, because at the end, you're going to deal with an optimization problem. And the optimization here is to find parameters, and these parameters theta you see here. So these are parameters of your theory, like the variational parameters you had in project 1, which was essentially just one parameter. Now, these variational parameters are those you want to optimize with respect to. So in your case now, the parameters are not the standard variational parameters in the wave function, but the parameters of a network. And then when you calculate the derivatives, then you have to actually take the derivative of this quantity and optimize that with respect to the parameters theta. So theta is a common container for the parameters you are going to optimize. When you optimize a probability, you are clearly interested in the maximum probability, right? There's nobody who's interested in the minimal probability. So when you want to optimize it, you want to maximize the probability. So that's a maximization problem. Now, normally you don't deal with products, but you take the log of a product. So you optimize that, and the log is a continuously increasing or continuously decreasing if you have a negative log. So that is ideal for this kind of maximization or minimization. So some people maximize the probability or maximize the log, or you can alternatively minimize minus log. So these are two equivalent problems. So if you prefer minimization, you take minus log of the probability. If you don't mind and like maximization, you take the max of, or you just take the positive log. So the problem with Boltzmann machines resides in this partition function, which is the normalization factor. So in our case, this F is simply going to be the exponential with the energy. But we make this energy is not the energy you're going to calculate for the system. That energy is a model which contains parameters. And that model defines the way you're going to treat these various probabilities. So at the end, what you want is this quantity here. Now, in the Monte Carlo calculation, we are a little bit lucky because we are not going to need this one. And we are not going to need what's also called the conditional probability, which is common in a standard Boltzmann machine. Because we are not going to optimize the probability, but we are going to optimize the energy. So that means that the function we optimize is different from a standard Boltzmann machine. So I just wanted to give you this so that you don't confuse yourself, because when you read about Boltzmann machines, what you typically do is actually to optimize. So in this specific case, what I did here was also to just change to this X and H, because if you deal with a standard Boltzmann machine, and I wanted to show you this on the whiteboard here, so let's just quickly do that. So when I write this X in boldface, this is now a configuration. And you can have, if you think of a standard Boltzmann machine, so let me just bring up the, just stop that one and just go back to the whiteboard. So for these Boltzmann machines, what you're doing then is that if you think of the probability P of X, and I'm just writing this as a vector. So this X can contain all the positions of the particles, or it can be a configuration. If you're familiar with the Ising model, this could be a set of spin values. And then we have this H, which is a hidden variable. And this is now given by a function f of x, of h, of theta, and divided by the normalization constant, where we have summed over all these parameters x and h. So z here depends on the parameters you want to optimize. So that means that z is now the sum over x and the sum over the h's. And then we have this function f of x, of h, of theta. And the standard choice, and this is why these are called energy models, is actually to choose an e to the minus e of x, of h, of theta. So this is now then called an energy model. Which means that you have to make a model for it. This is not the energy you're going to calculate. So then it means that we should put a tilde on top of it, just to indicate that this is not the energy of the system. But this is just a way to parameterize your trial wave function. So what a typical one, and I'm going to put a BB here. So BB stands for binary binary. That means that the x's and the h's take binary values. This could be, if you think of the Ising model, if you're familiar with that, and I guess everybody here has seen the Ising model. This is a kind of standard toy model in physics, which has been studied since 1926, more, yeah, almost 100 years ago. So in that case, you would choose this one as a minus, and then you have a sum of parameters, I. So this is A is a variational parameter now. It's the parameter of the network. And you would have an X of I, and then you have a J, and you have a new parameter, H of J, plus the connection between the two variables. So this is you can think of this as an interaction. So we could let this sum go from 1 up to m, and this go from 1 up to n. And this sum here goes over n and m. And then we have the xi's, some weights, wj, and then we have an hj here. So if you now look at these variables which we have introduced, these a, b's, and wij's, these are the parameters theta. So what we have is a container theta, which now contains a vector A, a vector B, and a matrix W. So A would typically be something which has a dimensionality m. B is a vector of length n. And obviously W is a matrix, and normally these are real, of dimensionality n times n. So these are the weights, and A and B's are the biases of the network, which means that your network is going to look like this. So you could have, if you have two particles in two dimensions, then you would have a node x1, x2, x3, and x4. And then you can decide how many hidden nodes you want to have. So these have parameters A. So this would have an A1, and the other one would have an A2, etc. So these are called the biases, and they're often initialized so that in case, to be different from 0, in case these weights are by accident 0, because else the training would stop. And you would have a B, a 1, you have an H1, H2, H3, H5, H4, and H5. So you would have a B1 here, you would have a B2 here, a B3. So these are parameters, B5, and you have an A2, A3, and A4. And then these are connected. So we have a connection between the different nodes from the visible layer and the hidden layer. So I'm just going to put up all these connections. And then we have that one, that one. At the end, it gets pretty messy, but you see the pattern here. So you would have a parameter here, which will be W11. And these are the weights. Now, you can make this model more complicated. You can actually have interactions between the nodes in the same layer. So you can have inter-layer connections and intra-layer connections. But that makes the model much more complicated to train. So what you see here is normally called a restricted Boltzmann machine. Restricted because you have only inter-layer connections. So this is the basic layout of an RBM. You can stack here, you can have more layers, but that makes everything more complicated. So if you have intra-layer connections, this is called a deep belief network. If you leave that out and you have only inter-layer connections and you make it deeper, then this restricted Boltzmann machine becomes a deep Boltzmann machine. But they are more difficult to train. So there's always a kind of balance we have to strike here. Now, if you look at this model, which we have here, this EBB, if we rewrite this in terms of a more compact notation, it means that this model EBB for vector X and H is something which, and I'm leaving out this theta just for simplicity. This is something you would write out then as minus. You have the transpose of the vector A multiplied with the vector X plus the transpose of the vector B times H. Sorry, this should be an H here. Plus the transpose of the vector X multiplied with the matrix W and multiplied with the vector H. So this is the more compact notation for the network model. So keep in mind that this EBB is not the energy of the system, so I'm putting a tilde on top of it. This is a binary model where the x's, an x of I, can take a value of 0 and 1 only, and h of j can take values 0 and 1. So this is a binary model. Now, in our case, we are going to replace the binary with a Gaussian binary. And you will see why it's called a Gaussian binary, because we want the x's to be continuous variables. And in our case, the x's are going to represent the positions of the particles. So then we want continuous variables. And we are then going to get a model which we are going to train in terms of a Boltzmann or Gaussian distribution times the distribution for a binary variable, which is typically often given by a sigmoid distribution. You will actually see that it becomes a sigmoid distribution. Now, one thing I wanted to mention here is that since these Boltzmann machines are a little bit outdated in the machine learning literature, what people have done is to replace this function E with a deep neural network. And when it comes to imaging, what you would train then could be a convolutional neural network. So instead of you calling this simpler binary function, you have just a more advanced deep learning model. And this has been extremely successful. And this is something which actually came right before COVID. People introduced these models. And the sampling, so this is a kind of digression which we are not going to deal with. You're not using metropolis sampling because that's way too expensive, especially since these are going to be multi-dimensional functions. So in our case, the metropolis sampling is reasonable to use because we are taking ratios between probabilities and we move typically one particle at a time. So that's a technical aspect which makes life easier. Now, in all of the Boltzmann machine training, since you don't want to deal with you producing this quantity here, this function f, for multi-dimensional probabilities, people have used what's called Gibbs sampling. So Gibbs sampling just looks at one of the variables at a time, given a fixed value for the other ones. That's called the conditional probability. And that is easier to sample from. But then you have to repeat this again and again in order to reproduce properly the distribution. So if you go to my lecture notes in a course called Physics 5429, I show how you can use Gibbs sampling, which is very efficient. And I have an example there where I take a multivariate a Gaussian distribution, 2 or more variables, and show how actually you can reproduce that distribution with Gibbs sampling. So you get the right distribution. So this is a technical aside. Now, when it comes to Gibbs sampling, like metropolis sampling, there are often long time correlations, which then makes the drive towards the most likely state a little bit more complicated. Now, in this machine learning literature, for the energy-based models, what people use now is another physics model, Langevin sampling. So if you're interested, I can show you and point you to the right references, but you're actually using the Langevin equation, which we encountered when we looked at importance sampling. So many of these models have a lot of, for the sampling itself, and also for the gradient methods, there's a lot of physics-inspired models which come in. So somebody from let's say, the machine learning community often has no idea where the Langevin equation comes from. But we know that as physicists. If you have taken a course in statistical mechanics, you have seen the Langevin equation. You have actually seen it in this course. So how many of you have taken a course in statistical mechanics? Well, that's good. Yeah. Statistical mechanics is, to me, the most beautiful course I ever took when I was a student. That was a clear eye-opener because I had a teacher in chemistry in the first semester, which just gave you all the equations in thermodynamics. And then you ask the teacher, what does Helmholtz free energy mean? And then the answer was, it's an equation, use it. Then I had statistical physics, and we started with a microcanonical ensemble. We went to the canonical one. We did the Legendre transformation, defined new variables, and then we could derive all the Maxwell relations, which relate all the statistical properties you see in thermodynamics in such a beautiful way. So to me, when I took statistical mechanics, that was finally, I'm doing something which has a beauty. And all of this, so this is my ranting about the way often statistical physics and thermal physics are taught, because you think you should have all the history with you. You start with Carnot machines and nobody understands anything. If you start with a microcanonical ensemble, you have a microscopic description of all thermal physics. Sorry for this, and this is my personal bias. And I think that's the way statistical physics should be taught. Okay, so when you see many, so sorry for going along this axis, but when you see these Boltzmann machines, it's all of statistical physics, the beauty which comes up. And you have all the concepts which you've seen. And like when people introduce these Langevin equations, so in the machine learning community, people often try different models. And somebody simply suggested to replace E with a deep neural network. That's pretty cute. Okay, so this was a kind of rambling from my side. Yeah, there's something. So let's go back to the slides. No, to the slides. And so I just wanted to use this as a kind of motivation for what you end up in standard Boltzmann machine calculations and the way they were done till roughly 2010. So what you would do then is simply, if you look at the probability, this is a function which you then want to optimize. And in our case, you're running over all these possible events which you have. So this could be a configuration of the system. Xi could be a specific position which all the particles take. Or if you think of the Ising model, which people actually used for this type of simulations. Back in 2017, there's a Science article, which has 1,000+ citations now. because it was really the first implementation of these things to quantum mechanics. Then these x's here would be the way you distribute the spins in the Ising model. So the Ising model, you can have spin up and spin down. If you have 10 spins, you have 2 to the power of 10 ways of organizing the spins. So one of the ways to organize the spins is one of these xi's here. Okay, with me here? Then what you want to do is optimize this quantity, and you want to optimize the probability. When you optimize the probability, you don't want to do the product, take the derivative of that, but what you do is you optimize the log of the probability, and that's an equivalent problem. And that gives you this equation here, which you're going to solve. Okay? Now, the problem which you have to face is you don't know this, the partition function. So as I said, if you go back here and you look at that one, if you now have just a simple case like the Ising model with 10 spins, 2 values, that gives you 2 to the power of 10 possible configurations. That means that this sum here, even for such a baby case, 10 spins, that's a baby case, has a sum which runs from 1 up to 2 to the power of 10. A more realistic simulation of the Ising model, which gives something which approaches more the thermodynamic limit, is a calculation where you would require at least 1,000 spins. And then you would have 2 to the power of 1,000. Even 2 to the power of 100 gives you 10 to the, 10 to the 36 possibilities in a decimal representation. So that means that this becomes an intractable object. And that was something which actually hindered a lot of the calculations in these cases. So what people did then is actually a trick. So when you look at this, you take the derivative of this function, and that gives you these 2 terms. And in the literature, this has been often described as a positive phase. And people have tried even to make models about this on the way people dream, for instance. So that this is something, this function here is a calculation, is actually a little bit artificial. But you need to calculate the derivative of the partition function, and you don't know that one. You don't want to calculate it. So what you end up doing then is to, when you look at the partition function, this is something you would calculate as an expectation value. So this function you can run because you have a model here. So you can simply run over all the events you're picking. So it's still a Markov Monte Carlo chain. But then for the partition function, which is a difficult object, you would use what you probably have seen when you introduce the free energy in statistical physics. This is actually the free energy. So you will often see in the statistics, in the machine learning literature, that they call this term here for the free energy. Another physics introduced concept. I really like these things here, actually. It's pretty fun. So if you take minus of this one, then you have the free energy. And you would calculate this quantity in this specific way. So if you look at the manipulations here, since you're also assuming that this function f is going to represent a probability. So that means, since you want this to be a probability, there is no point in looking at negative functions, right? Because the probability has to be positive. And you know also that if you have e to the minus something, this is a probability which is only 0 in the limit when the parameters go to 0. So which means that there's always a finite probability. And then you would typically replace this f with the exponential of the log of f. And then you can rewrite this calculation here. And you see now soon that when I rewrite this one, what you would get then is something which looks like this. And this is again your probability times that one. So that's the expectation value of the log of this quantity. And that's the way you calculate it in a standard Boltzmann machine calculation. And there are tons of approaches on how to estimate that one in the standard machine learning literature. So I'm mentioning this Boltzmann machine also because they were the forerunners of all generative models. And the thing which you see here, these equations which I put up, if you go back to this optimization problem you see here, this is at the heart of all generative models in machine learning. Because you're using a probability which you want to train. And training a probability leads to this type of equations. So whether you're using variational autoencoders or you're using diffusion models, stable diffusion, which is the new game in town when it comes to ChatGPT and generative models, it's all based on you having some model for the probability distribution, and then you trying to solve this equation in the best possible way. Now, forget everything about this, because we are not going to optimize the probability distribution. We are going to optimize the energy, and that makes life simpler. We are going to take the probability distribution, the Boltzmann distribution, as a model for the wave function. But that's going to simplify the calculations because we are more interested in the optimization of the energy. So when you do a standard machine learning calculation, you're optimizing the probability. That's the quantity you are training. We are optimizing the energy, and that's going to lead to some specific simplifications. Is that clear? So when you deal with a standard generative model, you will also need, for these neural networks which are training, you would need to have the probabilities for the hidden nodes and the probabilities for the visible nodes. And that means that you have to calculate the marginal probabilities. And then you have to set up a standard neural network where the different nodes fire or do not fire. And they fire according to a probability distribution, which in our case is going to be, for the hidden nodes, is going to be this quantity which you see here, but summed over the x's. And for the visible nodes, it's going to be this quantity. Now, the reason why Boltzmann machines are so popular is that for the different types of machines is that you can have analytical expression for this and analytical expression for that. And you will see that from the codes that this is actually what I have implemented. But we don't need this one. We can just integrate it out because we are optimizing the energy. So the only thing we are going to end up with needing is actually this quantity. So we will need expression for that. And that's the expression which I have coded in that example code which I mentioned last week. So I'm going to bring this up again. Okay, so let me just see here. Yeah, these are the quantities we want to calculate. And this is typically the energy models which we end up with. So here I put boldface to just indicate that that could be one set of positions or one set of spins if you're thinking of the Ising model. And then you would have something like this. Now, one of the reasons, so that's a probability distribution, but what we are going to do now is to sum over the h's after the break. And the thing which is also nice here is that when you're going to optimize the different quantities, so the analytical expressions, which I have programmed, when you use these simpler models like binary and binary Gaussian, is that you have very simple expressions for the parameters you want to optimize. So when you take this is one of the quantities we are going to need. So this E is that E tilde I had in the notes. It's not the energy of the system. This is just this function which I'm plugging in. And these are quantities which we will need to set up in the optimization. So keep in mind now that the parameters now are not the parameters we put in the variational wave function, but these are the parameters of a neural network. And we will need this type of derivatives. So when you have a analytical expression here, you can actually calculate these quantities. And what you see, if you take this one for a binary, it's pretty straightforward to see that these are the derivatives which we need to deal with. But we are going to take the input variables or the visible variables to be continuous. And then it's more convenient to do a Gaussian binary model. And this is the kind of thing which I wanted to discuss after the break, if that is okay. So I wanted to relate what we do with the way Boltzmann machines have been used and actually being used nowadays, except that nowadays we have a complicated neural network which replaces this energy function. But in our case, life gets much simpler because we are optimizing the energy, like we did in project 1. So I hope this detail gives you a better view on what these models are and how they have been used and how they are being used. So what I wanted to do now is to say a little bit about some of these simpler models and what kind of quantities we need to extract from them. And one of them, which you will encounter in case you don't want to do the Hamiltonian which we have put up, and you would like to study, let's say, the easing model, and link up with a paper by Carleo and Troyer from 2017. And if you want to reproduce that, and then a binary model is the one which you would use. And that is actually simpler than the one which we are going to use for continuous variables. However, the nice feature with the Boltzmann machines is that you have analytical expressions for the probabilities. So let me just bring up the binary case, because then you see the type of calculations which we need to do. And let me do that on the whiteboard here. So this is the energy model which we're going to have. And now we're simply going to switch here. So the quantity which we are interested in when we have this specific partition function, so let's just define that one. So we have a binary model. That means that our partition function is now given by a sum over x and h, and then we have e of a of t of x. So this is the model which we are making, and plus a b of t of h plus x transpose times the matrix which contains the weights and the hidden layer. That's the partition function. What we want is then the quantity, or if you haven't had time to write it down, let me just wait a little bit. This is the compact binary model. And the reason why I'm bringing this up is just to show you the type of calculations which we have to do. So in our case, we are going to replace the trial wave function with the trial wave function squared, which is now equal to the probability distribution. So in our case, psi of t squared is going to be proportional with this probability distribution for the x's and the optimal parameters theta. So in the optimization process, we are going to find the optimal weights and biases. So when I put a hat on it, that is the final optimal quantity which we're going to deal with. Now, in the calculations, what we will need then is actually this quantity here while we are performing the optimization. So theta is now without a hat. So when we perform the optimization, we will need this quantity here. And we are going to keep h as a binary variable. And we're going to have E of A of T of X plus B of T of H plus this X of T of W of H. So this is a quantity which we now want to sum away the hidden variables. So that means that what we get then is E of A of T divided with a partition function. And one of the things which is nice when you're doing the variational Monte Carlo calculation is that you always end up with ratios of the normalization constant. So in our actual calculations, like when you take the metropolis test, you have the ratio of probabilities, which means that the normalization constant disappears when we do the metropolis algorithm. So this ugly object, which we discussed before the break, is something which disappears in our equations or just factors out. So we need to perform this calculation here. So we would have a sum over H, and then we need simply to have the E of B of T of H plus X of T of WH. And this is something which probably, and you've probably seen this when you studied systems in statistical physics, is that you can rewrite this in terms of E of A T of X times C of theta. And then we're going to have a sum over the H's. And there's going to be a product of J, or rather, let's now just rewrite this a little bit more carefully. Let's take an intermediate step here. This is now given by E over sum over J. So these are the values of the hidden nodes. And then I have a sum, and it goes from J equals 1 up to N. And now I have a Bj plus, and I'm going to introduce a little bit more compact notation where I have performed the vector times matrix multiplication for X. So instead of putting in the subscript I and J, this asterisk here is going to mean that I have taken the transpose vector X and multiply that with its correct column. Sorry, this correct row. And this J is then just a row number, and this is multiplied with H of J. Okay? And this is something which we then can rewrite again, because we know that these sums over J's can be written out as a product. So I would simply have this term here, and I have the sum over the H's, and then I have a product from J equal 1 up to N. And then I have my E of a specific Bj plus this X multiplied with H of J. And I can actually rewrite this now, because now I'm looking at all the different hidden variables which I have. So this is something which I can then rewrite as 1 over Z of theta of E of A of A transposed times X. And then I'm going to have the sums of over all the hidden variables. So I have H1. So I'm just writing out every single component. And H1 could now be -1 or +1. I have only two values. So that could be 0 and 1. And then I have my product E of B1 plus this X multiplied with the correct row number or column, multiplied with H1. And this just goes on. And then I have H2 here, which takes value 0 and 1. And then I have E of B2 plus X. So this should actually be 1 here, 1, and then 2, and H2. And this goes all the way to the final node which we have. And then I have my H of N. And then I have E of B of N plus X transpose of N multiplied with H of N. Okay? And this is something which is actually not that difficult to calculate. And you know that if we put in values for H here, if I just take one of these, what you will get then is obviously one term where you have 0. So that's 1 plus E of B of N plus XT of W of N. And some of you have seen this function before. This is pretty close to what we call the sigmoid function. And that's going to give us the probability for the x's. And you see now that this is a quantity which we are going to have to program, because we are going to integrate away these variables h in order to get, because at the end what we want this probability, and that's the one which enters the calculation of the energy. Okay? Since in our case, we are not going to look at the probabilities to optimize, but we're going to optimize the energy, then what we will need to deal with is a function like this, which enters the standard energy calculation. And what you will see then, when you're doing the energy calculation, is that in our specific case, we need this quantity. We are not going to need the corresponding quantity where I have the hidden nodes here. So in a certain sense, what we are going to do is simpler than a standard Boltzmann machine calculation for generative models. Because at the end, we just need this quantity here in the training. So in a sense, it's actually different from the way you train a Boltzmann machine in machine learning. So in the slides, you will find the case which is a little bit more interesting for us, where we actually have continuous variables here. And that's a quantity which I'm just going to put up for you quickly soon, pretty soon now. So I'm just going to go back to the slides. So let's go back to the slides here and set that up. So in the example, so what you see now is actually just a repetition of what I put up on the whiteboard, but I wanted to slow down the pace a little bit because these kind of technicalities are those which we need to deal with. And you will see now that there is the same derivation which we discussed before. You will find it here in completeness. So this would be the probability which enters our optimization of the energy. And it ends up, you can find a similar derivation for the marginal probability, which looks like this. But we are not going to need that one because we're not setting up a standard neural network. Then when you do, this is more for the sake of completeness. When you do a standard Boltzmann machine, you need also the conditional probabilities when you're having nodes which fire and send an output. So you would also need, in a standard Boltzmann machine, you need to set up the conditional probability, the probability of H given X. So this is a little bit interesting, and I'm bringing this up because this is a quantity you then need to calculate. And then if you want to train a standard Boltzmann machine, you actually would need the outcome of Hj equals 1 or Hj equal to 0. And we know these quantities. That's a sigmoid function. So with a binary model, you actually get the sigmoid function for the probability for training the hidden nodes. And that's pretty neat. So there's a lot of nice mathematics, which also links well with a kind of physics intuition which you guys have developed over the years. So these are the on and off probabilities. And then you can calculate the similar ones for a probability like this with a given the nodes here, where you have the same expression. It's actually a sigmoid function. So if you have a binary model, the so-called conditional probabilities, which you would need to set up a full Boltzmann machine, is actually just given by functions you have seen before. Then the more complicated case, and this is where I'm putting up the equations for you. It's actually just a matter of going through the mathematics. So the kind of model which we make now. So as I said, this is not the energy of the system, but you can start with a model which looks like this. And it's pretty common to put these sigmas in case you don't want to evaluate the variance, just to put them to 1. That's a pretty common procedure. Then you have continuous variables for the x's, and you have discrete values for the h's. So h doesn't need to be a binary, but it's pretty common to have a binary. So a Gaussian binary, starting with this function here, is actually going to give you a Gaussian distribution for the x's and a sigmoid distribution for the hidden nodes. So this is just a rewrite of norm 2, by the way. This would be the parameters. There should actually be a minus sign here. There's a small typo, sorry for that. There should be a minus sign here as well. So the Gaussian binary is one of the models which has been used. And what you will see is that if you take a harmonic oscillator system with no interaction, you are going to get a Gaussian distribution, which looks very much like the harmonic oscillator wave function, because the harmonic oscillator wave function goes like x squared, e to the minus x squared. And that is why if you take the non-interacting case, the Boltzmann machine is going to give you the exact energy. So you can then take everything in project 1 and rerun with a Boltzmann machine for 100, 500 particles, and you will actually get the exact answer. But as soon as you take into account the interactions, then your Boltzmann machine is not going to be that good anymore. So now what we are going to do now is actually to set up the equations. So this Boltzmann machine is now going to be given by this product here, as you can see in this expression. And if we skip the partition function, the quantity which we are interested in is now the trial wave function. And just pay attention to the fact that I have taken away all the parameters theta, which are given by A, B, and W here. So again, you would sum away all the hidden nodes because you want a trial wave function. So the trial wave function is going to be proportional to this probability. And then when you do that, this is just the derivations, which I'm just going through here. So it's the same as before. So when we are now, in principle, we are integrating in this case, for this case, h is a discrete variable and it takes values 0 and 1. Whereas if you want the probability of h, then you have to integrate because x is a continuous variable in this case. So if you do that, you can also calculate the conditional probability for finding h given x. And similarly, you can find the probability of x given h. And again, it's the same exercise, except that now the equations are a little bit more complicated, but the mathematics is still doable. But you see now that if you include a more complicated probability distribution, then it's going to be not necessarily something which can be solved analytically. So often you search for ways which can give you an analytical answer for these probability distributions. And again here, you will see that for the h's, and this is not a big surprise, you get actually a sigmoid function as before. If you do the conditional probability for x's, I think I didn't put it up. Oh, that should. Okay, let me go to the Jupyter notebook, because in that case, let me do that one instead. Not that one. Why didn't that one go? Okay. Well, let me just try it again. No, I should have a network connection here. Yeah, that's on. Well, let me just get up that one. So let's scroll down a little bit here. It takes some time before it renders the mathematics here. Any questions while we are waiting? So this is just something which I suggested, but you can actually replace that Hamiltonian I suggest, and then take the same Hamiltonian you had in project 1. And instead of doing fermions, you can do bosons. So that is fully possible. And then you can do more particles. So it's very much up to you. And some people that previously what they wanted to do was actually to repeat the calculation of Carleo and Troyer. And then they replaced the Hamiltonian I suggest with an Ising model. So this is very much up to you guys, what you would like to study. Because if you have a flexible code, you can then plug in any type of Hamiltonian which you want to study. So one of the things, if you want to go beyond 2 fermions, then we have to look at the implementation of a Slater determinant, which is the next topic I will discuss after this. Okay, so I should have this one here down. So this is the Gaussian, and we have all these lovely steps here. So it took me some time to write down all the steps, and that's why I want to share them with you without harassing you guys. But what you end then up with is a probability distribution for the x's, which looks like a Gaussian. So you end up with a normal distribution, but where you have a different expectation value for the variance. So what you end up with is, and that's, you see the reason why this is called a Gaussian binary, is that you end up with a normal distribution with a mean value, which is given by this quantity here, and a variance sigma I squared. So the mean value now is given by this quantity, which you see here. So, but as I said, for the quantum mechanical calculations, there are many, many things which make life much, much easier for us. And this is what I wanted to say something about. And let me just bring up the slides in a slightly better way. I should have it. Let me just bring up this one. Oop. Sometimes these things disappear for me. Man. Here we are. Okay. Just stop it and then share again. Okay, sorry for this. So the thing which simplify life for us is now that the wave function which we're dealing with could now be, for the restricted Boltzmann machine, could just be this one, which is now the standard Boltzmann distribution. And then you would find the marginal distribution simply by what we have been discussing. So that is what we are used to see when we represent the wave function, and we would normally call that a neural network. So in this case, it's actually the wave function itself, which is equal to that one. Alternatively, so this would now be given by the product of all the hidden nodes. But this above wave function, so that would be the absolute value of the wave function, is the most general one because it allows for complex valued wave functions. But it changes fundamentally the probabilistic foundation of the restricted Boltzmann machine, because what is usually a probability in the Boltzmann framework is now an amplitude. This means that a lot of the theoretical framework usually used to interpret the model, graphical models, for instance, conditional probabilities and Markov chains, actually breaks down. So what is more common then is actually to make this approximation here. So if we assume it to be positive definite, so this is really an ideal quantity for bosons, then we can use the RBM to represent the squared wave function. This also makes it possible to sample from the model using, for instance, Gibbs sampling, because you can obtain conditional probabilities. In our case, actually the metropolis sampling is better. So I mentioned this in the previous lecture that Gibbs sampling means that you have to calculate these conditional probabilities. But in our case, we can now simply just use the wave function squared. And that means that the trial wave function we will put into the Monte Carlo machinery is actually given by what you see here. And this is something we can calculate analytically. And this is also what you will see in the program, because in the program, I have actually performed these calculations here. And you will find the final expressions in the slides. If you go into the Jupyter notebook, you have all the details. And this is more the kind of way you would approach it. So that means that your probability now is simply the wave function squared. And this is the local energy. And the only thing we do now is that we plug in this new wave function, which is the square root of the probability. And the thing we have to optimize is actually this one, as before. So we are not optimizing a probability as we would do in a standard Boltzmann machine. And the parameters, so this is the quantity, the gradients we want to drive to zero, as before. So the only thing we need to do now is simply to go back and replace our previous wave function with something which looks like this. And then we need to optimize these various parameters. So if you're dealing with the Ising model with, let's say, 100 spins, which you could easily do here, then these A's would go up to 100. You can decide how many hidden nodes you want to have. And then clearly, depending on that one, if you have 100 spins and you have 10 hidden nodes, then this matrix would have dimensionality 100 times 10. And then you will simply have 1,000 weights to fit. So compared to what you did previously, your optimization problem becomes more massive. So previously, you just had one parameter to optimize. Whereas now, it's the neural network which is set up, which defines the number of parameters. And you will see in that example, which we have in the Jupyter notebook, that I'm taking two particles in 2 dimensions. So that gives 4 input nodes. And then you can use the number of hidden nodes as a variable. And the thing we need to program then, when we are calculating these derivatives, we use, again, this is one of the expectation values which we are calculating. And alpha I is just a container for all these parameters. So as you did before, we need to calculate this quantity here, and we also need to calculate this quantity. And this is something we can easily calculate, which now depends on Z here. And then we have the parameters here, and then we have similarly for the weights. So this is something which we need to code in our program. Yeah. Yeah.
In effect, when programming side,
yeah,
we can, in essence, just neglect.
Yeah. Yep. Exactly. That's also another one of the simplifications. As I said, there's a lot of neat mathematics in the Boltzmann machines. And then what we have then when we take these derivatives is simply these expressions here, and we need to set them up. So if you go back a little bit to what we discussed before the break, so before the break, and I'm gonna go quickly back to that. So let me just bring that up here again. So before the break, we looked at the binary case. Let me just bring that up here. There's a lot of additional information here which you don't need to look at. This is more background information. But what we had before the break for the binary case, and this E is this function e to the minus, which we have. And so this is one of the derivatives we need if we have a binary case. So that was for the binary. But what we end up with when we are looking at the derivatives for the final trial wave function, so let me just bring that up again. So these are the quantities which we need to program. And as I said, normally you put this sigma to 0. And then we would have the weights, the bias is B and the bias is A. And this would be the expressions which we need to set up when we are calculating the derivatives of the trial wave function with respect to the variational parameters, which now are the parameters of the network. So these are equations which we need to have, and you will find them in that simple example code which we have in the Jupyter notebook. And this is actually what you have in the code here. So let me just switch back to that. So as I said, the kind of quantities which we need to deal with are actually these quantities here. That's the final equation for the derivatives. We have the log of the function here, and then we need to optimize this quantity. So that means that when you look into the program now, you will see now that I have these different parameters in the calculation of the wave function. And this Q here is actually that factor which I have defined. Let me get back to that a little bit later. But here, I'm setting up the wave function for the different particles, and then I also sum over the hidden nodes. So I'm actually performing that summation. I'm summing away the hidden nodes, but the parameters for the hidden nodes, they actually enter into this factor Q here. And the local energy then, so this factor Q is defined. I have it, where did I plug it? Here it is. So this is actually something which now gives you the argument to the sigmoid function for the hidden nodes. So if you look back at the equations, you will then recognize the different terms which we have to program. I take also the derivative of the wave function, and here I'm setting up these various derivatives, which I put up in the slides here. So they enter down there. And if you look into the equations, you will retrace all the different forms. So this QFAC is actually the term which you see in here, this one. And this is a code which we did run last time. It has the same elements as before. So except that now we have slightly different wave functions. and a slightly different local energy because we have a different wave function. That's the basic difference. And then the rest is as before. I also calculate the analytical expression for the quantum force, but the rest, the energy minimization part, is the same as the one which we had before. And the calculations of the integrals which enter the derivative of the wave function of the energy with respect to the variational parameters. And this is a simple case which you could just run if you want to. Use that as an example code if you want to. And in this specific case, you see now we have 2 particles in 2 dimensions, and then you should get exactly 2. And this is what it gives. And the gradient descent here is just the most simple one you can think of. It is just us setting up a plane gradient descent with a learning rate of 10 to the minus 3. So in a certain sense, the only thing you need to do is to adapt your code to the new trial wave function. That's essentially what needs to be done. So you see the calculation of a quantum Monte Carlo method with a Boltzmann machine is actually simpler in a certain sense than the optimization of a Boltzmann machine for machine learning, because there you have to take the derivative of the probability distribution. Whereas in our case, we are optimizing the energy. So this energy is our so-called, for those of you familiar with machine learning, this is the so-called loss or cost function, the function you optimize. And that makes life a little bit simpler. So I hope this kind of tour has been able to put things in a context. I know that many of you have taken a course in machine learning. For those who have not done, I hope you can see the wood for the trees here. Any questions so far? I spent a little bit more time on this material here because I think it's important actually to see the overarching things we are going to end up doing. Yes, Luigi.
So, this connection asks
So this is a very good question, actually, because the distribution we have now is not physically inspired, except that if you have a harmonic oscillator, non-interacting part, the Gaussian distribution has some elements of the physics of the system. However, that wave function you see here, which you have set up, in case you have a divergence in your interaction, when 2 particles are getting close to each other, like a Coulomb type of interaction, then this trial wave function will not catch that divergence, because there is no way you can cancel the divergence in the potential energy with a similar one from the kinetic energy for 2 particles. So you're missing this term which we put up, and I can put this on the whiteboard here. So let me just bring it up. So this is a very good question. And that means that when you look at the trial wave function, what you can do is to take the Boltzmann machine as a starting point, and then you can multiply that one with more physics. So you can think of a Boltzmann machine as something which gives you a starting point. So just to remind you, if you look at this 2-electron case which we have, or any type of systems of 2 particles which interact, so with 2 interacting particles, there is a divergence in the kinetic energy, which goes like this is the relative distance between 2 particles. And this is given, so you can rewrite Schrödinger's equation for 2 particles in relative coordinates and the center of mass. So you can make a transformation from R1 and R2 to to the relative distance. So this R12 is the relative distance between two particles, and then the central mass. The central mass is simply position of 1 plus 2, and that cannot be 0 unless R1 and R2 are 0. Also, the interaction does not depend on the central mass, but it depends only on the relative distance. This is pretty common for any kind of physics interactions. So what you would get then would be something which goes like, and now this is very schematic, R12, and then you have a trial wave function which depends on the relative coordinates, and you want these two to actually, in the limit of R12 goes to 0, you would like these two guys to cancel each other. So this is what you would call a minimal physical requirement on your trial wave function. So in order to cancel these two divergences, you can see now that this is a famous differential equation. You get a way, this comes from the kinetic energy. When you rewrite the kinetic energy in terms of relative and central mass. So it's actually the kinetic energy of two particles, where I've put away the central mass piece, which just gives me a constant and doesn't cause problems because the interaction does not depend on that. It depends only on this one. So when you do that, you can solve this equation because you get a famous differential equation, which simply says that d R12, and now I'm just multiplying away the minus signs of this psi of R12 is equal to psi of R12. And this is an equation we know how to solve, which means that psi of R12 in this case has to be proportional to E of R12. If you have an attractive interaction, you have a minus sign in front of the interaction, and you get a minus sign. So if you think back to the hydrogen atom, if you just think back to that one, where you look at the position of one particle only, one electron, which is your degree of freedom, then you know that the solution, the analytical solution to the hydrogen atom, if we just take that one, that contains a set of polynomials, which are called the Laguerre polynomials. So you can solve that analytically, you probably remember that. There are some quantum numbers here, which reflect the number of nodes you have, and also the orbital momentum. So I just put that in a container alpha. And this depends on R. So these are Laguerre polynomials. So this is the analytical expression. And then you have e to the minus R. And sometimes you see this with a factor of a half, a scaling or so on, but just let's take that one away. And then you have something which you call a polynomial, an additional polynomial, which reflects the angular degrees of freedom. And these are normally given by hyperspherical harmonics, which then contains an exponential multiplied with another famous polynomial, a so-called Legendre polynomial. So you have two of these famous French mathematicians, Laguerre and Legendre, which then enter the definition of the problem for the hydrogen atom. So this will contain N, L, and ML, where N and L are this quantum number alpha, and that depends on your angles theta and phi. Okay? So if you choose angular momentum or orbital momentum 0, then this P is just 1. If L is 0, then this function here is just 1 over square root of 4 pi. And then it's isotropic in space. This is a so-called S waves. And then this factor which you see here has the same, this one has the same origin as what you saw here, except that then you have a minus here, and then you have an R here. So it's the same differential equation. So that tells you that the physical content, the minimal physics which you can bake in, should have a wave function which goes like that, or like e to the minus r. We can put in this by hand with some variational parameters. And what you will see then, like the wave function which I put up in the different examples we run through during the semester, you probably saw that I had this trial wave function for a harmonic oscillator case, R1, R2, which was given by harmonic oscillators. So I had some constant, which I'm just calling for C, and then I have E of minus, and then we have a parameter alpha squared, and then I have R1 squared plus R2 squared. That's a harmonic oscillator. That's a single particle piece. And then I have this E of a parameter beta. I could write it like this. So there are many ways of writing it. Or alternatively, I could just write it like E of beta times R12. This is a minimal way to bake in the physics. So I know it's moving in a harmonic oscillator trap. That means that I should have this term, because that's the harmonic oscillator. So when I take a Gaussian binary, I have this, but I don't have that. If I, on the other hand, were to take this Boltzmann machine and study the hydrogen atom, then I would like to have minus alpha times R. So this would not be a good choice for the harmonic oscillator. And then you would have to cook up another type of Boltzmann machine. Alternatively, what you can do is you can think of the Boltzmann machine as just something which gives you flexibility to fit parameters. And you could multiply the Boltzmann machine with some physics information like this correlation part. So you will see that when you run the same case, and as we saw last time, when I now don't, when I include the interaction, I don't get very good results. And that's simply because my trial wave function is not good enough. So one thing you can do then, you could say, oh, maybe I should have more hidden layers, or I should have more hidden nodes, and so on and so on. But still, you won't have a part of your wave function which cancels these divergences. So this has a name. I don't know if you have it. We mentioned that some time ago. So if you just think of this term e to the minus r, and you plot that in one dimension. So in one dimension, when you plot it, so this will be plus x and minus x, your wave function is going to look something like this. And this in English is called a cusp. So some of you may have encountered that wording in quantum mechanical studies. It's called a cusp condition. So the cusp condition is simply that your wave function should be able to catch the cancellation of this term with that term. So you have a divergence from kinetic energy, which cancels the divergence from the potential energy. This also tells you why you cannot solve a Coulomb type of interaction problem in one dimension, because the one-dimensional kinetic energy does not contain this term here. So you cannot solve analytically a Coulomb problem in one dimension, and you see that immediately from that case. If you rewrite your kinetic, what we've done here is actually to rewrite the kinetic energy in spherical coordinates. And then we're looking at the relative distance and the central mass distance. Okay, so this is a very good question, and you will, when you add interactions, unless the interaction is very, very weak, it won't give you exciting results. And that's why the next step would be to include a neural network. But that is a good fraction of a master thesis. So some of the things, but think of, if you take this Boltzmann machine with what you have developed, and instead of doing the problem which we suggest here, and you take the Ising model, you will actually reproduce the science article of Carleo and Troia in 2017. And that is a very well-cited paper. So you could say that in this course here, we actually can reproduce scientific articles just from a few years ago, which made a big impact in the literature on quantum mechanical simulations. But you see the limits of Boltzmann machines. You see they're easy to implement. You can use all the variational Monte Carlo machinery. And that was the streak of genius of Giuseppe Carleo when he published that paper. that he saw clearly that the Boltzmann machine could easily be applied to things like the easing model. And that really opened up the ground for simulating quantum mechanical systems with deep learning methods. But everything we do has its pros and cons. And that's perhaps the most important thing, which you can take as a takeaway message from this course. We can simulate things, but we have always to keep a critical eye on what we get. So next week, what I wanted to do, I was planning to say something about Slater determinants, but next week I wanted to discuss how you can implement Slater determinants. And that will be basically the last topic this semester. And then we will use the rest of the time just discuss the projects. Any questions so far? Okay, let me just switch off the recording in the meantime.